Hello, my name is Michael Whittington, and my project is titled Predictive Analysis for Injury Diagnosis and Localization. This is a brief outline of what is included in this presentation, which features an overview of the project and data, the exploratory data analysis that was conducted, the machine learning models leveraged and their results, the 2 applications that were completed, and then we'll wrap up with conclusions and future steps. Each year, the U.S. Consumer Product Safety Commission provides an injury data set, which is collected by their system called National Electronic Injury Surveillance System, or NEIS. The goal of my project is to use this data set to find patterns in the data and accurately predict both the diagnosis of a patient's injury and the body part where it occurred. Ultimately, by understanding these injuries, companies can make safer products and doctors can treat patients faster and better. This helps in making products safer and improving medical care for everyone. Here's a brief overview of the dataset that I will be using. The dataset is fairly robust, featuring over 300,000 rows and 25 columns, where each row represents a patient that went to a participating hospital's emergency room, specifically in the year 2022. Outside of using some of the typical Python functions, like dtypes and describe, when exploring the dataset, I leveraged helpful libraries like Pandas profiling for an overview report and a report on my target variables, as you can see, and then also using Plotly for developing a correlation matrix of all the features in my dataset, and more specifically, giving me the ability to key in on the different features that more directly correlate to my primary target variables of body part and diagnosis. In an effort to further my exploratory data analysis on not only this project, but also on future datasets, I developed an application that can ingest that dataset and automate much of the EDA process. I will now demo that application. The creation of this application was done using Streamlit and the other technology that is shown on this slide. As you can see, the application offers a wide range of EDA services. And just to showcase some of those services, you can see that immediately you are able to drop in your own file here, and that can be either a CSV or Excel. And then also, once that data is uploaded, it will give you a select number of options where you can choose different visualizations that you want to see. For this demo, I'll be showcasing the data frame, which shows the rows and columns within your data set. The descriptive analysis piece, where you can instantly analyze some of the key information about your data set. You can also visualize the distribution of specific numerical columns, and in this case, we chose our 2 target variables of body part and diagnosis, where we can look to see a histogram and a count of where each feature has the most most count. Additionally, we can visualize box plots, and in this instance, we can also look at our target variables and determine some outliers within our data set. Once the EDA and data cleanse phase of the project was complete, I was able to start training and testing different machine learning models. The train test split used on this project was 80-20. The models that were tested include Random Forest, XGBoost, LightGBM, CatBoost, and KNN. There were other models tested, however, that produced poor results and therefore were not included in this presentation. In addition to running the models, I tested different improvement methods in an effort to unlock the full potential of these models. Those methods include hyperparameter tuning, cross-validation, feature importance, and stacking and blending. Getting into the results of the model, we look at how accurate the model was at, or the proportion of correctly predicted observations to the total observations. KNN performed the poorest, while XGBoost performed the best across the board. While gradient boosting did not perform well enough to be presented on this graphic, advanced implementations of it seem to perform fairly well. Random Forest also performed well in comparison to the boosting models. Taking a deeper dive into the XGBoost model, we can see that the classification report shows that when predicting the diagnosis, the model outperforms compared to predicting the body part. This holds true across all method metrics in the classification report. When predicting diagnosis, 10 of the 30 classes perform well, with an additional 10 performing moderately. On the other hand, the body part predictions only had 2 classes that performed well. I also want to point out that body part 75 was one of those high-performing classes. This body part is classed as the head of the body and has the most occurrences in the dataset. Additionally, I wanted to show the results of conducting feature importance for the XGBoost model. For predicting diagnosis, this does share some surprising insights. Primarily, age and sex don't play a more important role in predicting the diagnosis. However, when it was tested, these ultimately did not alter the prediction accuracy very much at all. The body part feature importance results are very similar to the diagnosis feature importance results. The main difference is that fire involvement and disposition play much less of a role as features for the body part prediction. I will now demo my application, which allows the users to enter information, and the application will provide the top 3 likely body parts injured and the top 3 predicted diagnoses. The creation of this application was done using Streamlit and the other technology shown on the slide. Here, I will demonstrate 2 different prompts and show the results. For the first prompt, I will use information about myself. When typing in my own information and also adding electric blenders as the issue, and then also showing that the injury occurred at home, we can see that the top 3 predicted body parts injured are finger, lower trunk, hand, and the top 3 predicted diagnoses are laceration, other, strain, sprain. And when looking at these results, they make sense. When using a blender, you often might, if you had an injury related to it, would be injuring your finger. Or perhaps you dropped the blender and you injured the lower part of your body. And of course, obviously, the finger is attached to the hand. Next, we will do another prompt for, let's say, a 64-year-old female that is of Hispanic, other. For this one, we'll choose a different product. Let's say this person was using a water slide in their pool at home. When we look, the top 3 predicted body parts injured are wrist, head, lower trunk, and the top 3 predicted diagnoses is fracture, other, strain, sprain. And when you look at diagnoses, you can see that they would align with what might happen with your wrist or, your lower trunk. Now, to close out this research, I want to discuss some of my findings and potential future steps for this project. When predicting the 2 different features, the model's diagnoses predictions significantly outperformed the body part predictions. When applying common data science techniques for model improvement, the results showed limited improvement. Based on the achieved results, we can likely determine that there may lack a clear pattern or distinction between classes. Finally, I think a crucial lesson in data science is that, you have to be prepared to not get the results that you were expecting, and this can happen. The reason I said we can likely determine that there may lack a clear pattern or distinction is because without including more data from past years, I don't think we can officially make that determination. That's why I think a crucial future step would be training and testing these models on more data. Now, in order to accomplish that, the research would require more compute power. During this research, I ran into compute constraints because of the size of the data set. More compute would allow for a more thorough analysis of this dataset and the hyperparameters of the models. Lastly, there are other evaluation metrics outside the ones evaluated here that could show more information into the reasoning behind the results. And with that, I would like to say thank you so much for listening to my presentation, and I look forward to presenting any future developments of this research.